we're going to cover solving equations with trig functions. I should say we're going to move beyond the trigonometry, but only in title. Everything we do from now on is going to involve some trigonometry. What's going to really help here is if you think about how we used to solve equations with x's, right? We get some expression in x's, we try and get the x on one side. There are a number of techniques that we've used, things like the quadratic formula or factoring. Those are all going to be helpful, but now we have a trig function to deal with. So I'm going to show you how we do this, but I'm going to start with just a very simple example. We're just going to look at sine of theta equals a half. We've done something like this before. Well, here we want to get theta by itself, but that's not a problem because we can just use the inverse function. We can take the inverse sine of both sides. On this side we'll be left with theta, and here we'll have the inverse sine of a half. But as you might guess, there's not going to be a single solution here because the sine function is periodic. That's going to be generally true. There could be multiple solutions having to do with periodicity of these functions. So a good place to start is where is the sine equal to a half in the unit circle, in the first 2 pi? Well, if we want the sine to be a half, well, we should recognize that this is a 30, 60, 90 triangle. So this is going to be 30 degrees or pi over 6. So theta pi over 6. But this is not the only place where the sine is a half. Because the sine is the y-coordinate, we can just draw a line across here and see that there's going to be another place where sine is a half. And that, of course, will be the supplement, which is 5 pi over 6. Okay, so those are 2 solutions. But we reach each of these solutions every time we go around the circle. So really, we have theta is pi over 6 plus 2 pi n, and 5 pi over 6 plus 2 pi n. That's a very typical thing that will occur. You'll get 2 solutions and plus all the sums where you add 2 pi n. Occasionally those will match and you can coalesce them. But, so that's what the solution to this simple problem looks like. And most of the other problems we'll look at will descend to this at some point. We'll end up with some trig function equal to a value, or maybe we'll have 2 different versions of that, and we'll have to go through this process. Find all the solutions. All right, this was a nice problem in that we know what the sine of, we know that the sine of 30 degrees is a half, so it worked out a little more easy than if it was just some random value. But let's take a look at a problem where you won't have that. You need to use your calculator. Let's say instead of some nice value, we have the cosine is equal to 0.65. Or theta is the inverse cosine of 0.65. That's radians. No, that's not radians. Theta is radians. Okay, so we can use our calculator here. We can find that this is approximately 0.863. But again, this is, we're going to find that there are two solutions in the first 2 pi. I'm just going to draw, an approximation here, so we know that the cosine here is cosine here is 0.863. But since the cosine is the x-coordinate, we know there's going to be another value down here. Sorry, this is 0.65 is the cosine. 0.863 is the radian measure of the angle. So we know there's another angle down here. We could look at this as either negative 0.863, or we could look at it as 2 pi minus 0.863, which is about 5.42. So here again, we have our two values, theta equal 0.863 or 5.42. But again, every time you go around the circle, you're going to get solutions. So it's really 0.863 plus 2 pi n and 5.42 plus 2 pi n. Now, let's say you don't have a calculator, or let's say you're explicitly told to leave an exact answer. These are not exact answers, these are approximations. We could substitute back in here. This could be theta equals inverse cosine of 0.65 plus 2 pi n. And then again, here we could have 2 pi minus cosine of -1, cosine of inverse cosine 0.65 plus 2 pi n. And then we would have all the solutions listed, as exact values, even though we can't resolve this to an exact value. Okay, that's how we solve these basic equations. That's what all our problems are going to come down to, but some of them will be more complicated. So let's take a look at an example where you would have to do some factoring. All right. Recall that if I had an equation like this, if I had x squared minus 2x equals 0, that I can factor this. I can just say that's x times x minus 2 equals 0. And that tells me that x could be equal to 0, or x minus 2 equals 0, meaning x equals 2, both solutions. In a similar vein, we had an equation like this. 5 times the sine of theta cosine theta plus 4 cosine theta equals 0. Well, at first blush, that looks impossible. We have no way of dealing with this, combining these. But it's actually very simple. If I simply factor out cosine of theta, I'm left with 5 sine of theta plus 4 equals 0. And I can use the same strategy, right? If the product of these equals 0, then if either of these are 0, I'll have a solution. So now I'm back to cosine theta equals 0, or 5 sine of theta plus 4 equals 0, which just means sine of theta equals -4/5. Now, both of these problems are like the first two problems I showed you. Theta here is the inverse cosine of 0. Well, where is the cosine 0? Cosine is 0 at 0. No, it's 1 at 0. Pi over 2, and also 3 pi over 2. But we would want to include periodicity tests.
I'm not feeling well. Can I be excused?
Oh, of course.
Thank you.
Of course. So we would have pi over 2 plus 2 pi n would be solutions, or 3 pi over 2 plus 2 pi n would be a solution. But we also have this possibility, that theta is the inverse sine of 4/5, -4/5. Okay, well, that again is a calculator problem. This is approximately 0.927. But again, the complement of that, 2 pi minus 0.927 would also be a solution. So this is approximately 2.21. So we end up with all these solutions, 0.927 plus 2 pi n and 2.21 plus 2 pi n. So we have all of these as solutions to this equation. Are we okay so far? Because it's just going to get a little trickier here. Not too much. Yes.
For that, the sine theta equals -4/5. Is that staying like where it would be in the fourth quadrant? Like, since it's a negative, is that saying it would be negative, or am I kind of like misunderstanding that?
Oh, I probably made a mistake. That should be just the number that comes out of your calculator. Keep pushing the wrong button here. $53. What does that mean? Means I'm in the wrong mode. Try it again here. It's negative 0.927. Okay, negative 0.927. Let's see. This is negative 0.927, or 2 pi minus 0.927. So the other value is going to be over here. So what's that going to be? That's going to be pi plus 0.927. All right. So what's that going to be about? 3.14 plus 927. I don't know. We'll say 4. Thank you. It does take a little working with these to get an intuition that something's wrong. So if you notice that, that's a good sign. All right. Moving on. So now, let's take a look at another problem we're going to have to factor. 2 cosine squared theta minus 7 cosine theta plus 3 equals 0. All right, well, we're not going to have a simple factoring here. It might make sense to take, to make this look more familiar, to just substitute here x equals cosine of theta to get something we're more familiar with. Okay. Well, that's something we should be familiar with, right? Either we're going to factor this using reverse FOIL, or we could use the quadratic formula. It turns out this will factor nicely. Okay, minus 2 times 3 is 6, plus minus 1 is minus 7. So we're going to get out of this x, or cosine theta, equals 1/2, or cosine theta equals 3. Well, this is pretty straightforward now. We did one just like it at the beginning with sine, so I'm not going to repeat that. We're just going to get pi over 3 plus 2 pi n and 2 pi over 3 plus 2 pi n. What about cosine theta equals 3? What kind of solutions are we going to find there? Make a mental note to put on the exam. Cosine of 3 is 0. Cosine of theta equals 3. Yeah. What values of the cosine can give us 3? And why not? Yes?
Well, when I put it in the calculator, it says that there's an error with the domain.
Yeah. What's the domain of the cosine? I'm sorry, what's the range of the cosine? The domain of the inverse cosine. Yeah. Okay, so think about this here. The cosine kind of looks like this. Its domain is all real numbers, but its range is just minus 1 to 1. So now when we look at the inverse cosine, which, how does that look? Having trouble visualizing it right now. So this point is going to go over here. And this point is going to go up here. I'm just out of luck today. Do anything right. Can't even get it out of graphic mode. It's in radian. Maybe it wants to be in degree mode. That sounds possible. No. We want to be in radian mode. Looks like this. All right. Okay, so this is the inverse cosine. So what's its range and domain?
All the numbers? All the numbers?
The domain? This is it. It doesn't go any further. It's not periodic.
So -1 is 1.
Yeah, domain is -1, 1. The range and domains of inverse functions will switch. Now, this, of course, is not the range of this function, right? Because we have to truncate this to get a function here. Otherwise, this would kind of go like this, and it wouldn't be a function. So in the case of the cosine, we're going to go from 0 to pi, right? You should know these for the various sines and cosines and tangent functions. The domain and range of the actual function and the inverse function. All right, so that's why, where were we? That's why you don't get something with cosine of theta equals 3 or inverse cosine of 3. It's not in the domain of that function. So there are no solutions, right, from this part of the equation. All right.
Question.
Yes.
Should the other part of the, I guess, domain for the solution for cosine 1 over 2, would that be 2 pi minus pi over?
Yeah, probably. Let me take a look at this. So if the cosine is a half, that means, yeah, what did I put here? 2 pi over 3? We could just put negative pi over 3. Or 5 pi over 3. Same thing. Thank you. Can you come to my next class and keep me honest? All right. Okay, any questions about how we did this? right? This was nice because we could, you know, get a nice easy factor out of it. That might not be the case. Let's take this for example. 9 cosine, I guess this is a negative side. Cosine squared theta minus 6 cosine theta minus 1 equals 0. Or again, don't feel shy about rewriting it this way if it makes it easier. 9x squared minus 6x is 1 equals 0. Well, what's the determinant on that? It's 36 minus 4ac, but there's a minus, so it's plus 36. So the square root of 72. So it's not going to factor nicely. So, you know, we need to use the quadratic formula here. So that tells us it's negative b is 6 plus or minus the square root of 36 minus a minus 4ac plus 36 over 2 times 9, 18. And that becomes 1 plus or minus the square root of 2 over 3. Well, you know, fool me once, shame on you. I'd like to know what 1 plus or minus the square root of 2 over 3 is. 1 plus square root of 2 divided by 3. So approximately 0.8. That's good enough. And then 1 minus the square root of 2 divided by 3, approximately negative 0.14. Well, I did that because I want to make sure those are in the domain of the inverse function, right? So I have cosine of theta equals 1 plus the square root of 2 over 3 and 1 minus the square root of 2 over 3. So my theta is inverse cosine of 1 plus the square root of 2 over 3 and cosine inverse of minus the square root of 2 over 3. Well, now we have to look at the fact that each of these will have 2 values in the unit circle, right? So if we have 0.8, where will 0.8 be? Well, pi over 2 would be 1.7, so that would be in the first quadrant. So we'll also have the negative of this. And this guy is negative 0.14. It's over here. So we'll also have n plus 2 pi, right? Did I do that right? I think I want the negative here. And then the negative of cosine negative 1 minus square root of 2 over 3. And then all 4 of these are going to rotate around, so we can add 2 pi n to each of them. So as you can see, you can get a lot of solutions in one of these problems. So all of these problems have had the feature so far that either we just had one trig function, or in a previous case where we had sine and cosine, they factored into separate parts. That might not always be the case. A problem that the book gives us. So here we have two different functions. We could rearrange this a little. We could say cosine theta minus sine theta plus 1 equals 0. That doesn't really seem to help much. Problem is we have two different functions here that we don't really have any way to solve for directly. And that seems to be what makes these possible, that we end up just with some trig function equals some value. So we're going to have to think a little harder here. Well, if I had tangents or secants or cosecants or cotangents, I can convert them into sines and cosines. But I still might end up with a cosine and a sine. And I might need to do a little more. So how can I convert one of these, sine or cosine, into the other? Well, we have an identity that might help us. We have the Pythagorean identity. Right? So how does that help us? Well, you can see here, we could solve for sine of theta, or sine of theta equals the square root of 1 minus cosine squared theta. Okay, well that's gonna at least solve that initial problem. Right? Now I have cosine of theta plus 1 equals square root of 1 minus cosine squared theta. Now I have a new problem, how to combine this cosine and this cosine under the square root sign. But if I was just dealing with the variable x, it might be more obvious what I need to do. Does anyone have a suggestion? I want to solve for x here. How might I do that?
Square both sides.
Yeah, square both sides. When I do that, I want to be a little careful. Remember, this can introduce a phantom root sometimes. Let's go ahead and try that. X plus 1 squared equals 1 minus x squared. Or x squared plus 2x plus 1 equals 1 minus x squared. 2x squared plus 2x equals 0. Or 2x times x plus 1 equals 0. Remember, this was really the cosine of theta here. When you get a problem like this, if it helps you, to make it less confusing to remove the cosine for the time being, go ahead and do it. Just make sure you remember at the end what this tells us. It says x is 0, meaning cosine of theta equals 0, and x equals minus 1, or cosine of theta equals minus 1. So now we have to think of where is the cosine 0. I think we did that already. Theta is going to be pi over 2 plus 2 pi n, and 3 pi over 2 plus 2 pi n. And where's the cosine minus 1? Think about that. Where's the cosine minus 1? Yes?
Pi.
Yeah. Theta can be pi plus 2 pi n. Now, at this point, we might want to check to make sure that we didn't introduce some tangent here. So let's just try pi first. Cosine of pi plus 1 equals sine of pi. Well, cosine of pi is -1 plus 1 is 0. The sine of pi is 0. So this is good. Let's look at pi over 2. Cosine of pi over 2 plus 1 equals sine of pi over 2. Well, cosine of pi over 2 is 0 plus 1. Sine of pi over 2 is 1. So this guy is good. And the only thing left is cosine of 3 pi over 2 plus 1 equals sine of 3 pi over 2. It's the sine of 3 pi over 2. -1. So we have 0 plus 1 equals -1. So we introduced a phantom root. We know that this is no good. That's probably as tricky as we're going to get. At least in terms of having to solve these. There's one more case you have to look out for. There's one more eccentricity about these types of problems. Everything so far we've seen, once we had values within the unit circle, because of periodicity, we could just throw in that plus 2 pi n. I hope you realize if it was a tangent function, it would be pi n, because the tangent is pi period, as pi is its period. But we could get a problem that works a little differently. Let's take a look at just a simple case. 2 times the sine of 3 pi minus 1 equals 0. Or sine of 3 pi equals 1/2. Well, there are 2 ways to go about this, but before we start, let's first pay attention to what's different. What's the period of sine of 3 theta? You know that for sine of 2 theta, the period is 2 pi. Why did I write that? The sine of theta has period 2 pi. So what about the sine of 3 theta? Remember that equation I wrote? Y equals A sine B times X minus C plus D. When we were graphing, this is an amplitude, this is a vertical shift, this is a horizontal shift, but what does the B tell us?
Period?
Tells us the period, yeah, but it's not the period, right? Period of, this is not 3 theta, just as the period of this is not 1, it's 2 pi. What's the relationship between B and the period?
2 pi.
Yeah, it's 2 pi over B, or the absolute value of B. So that tells us this, the period here is going to be 2 pi over 3. Again, remembering if it was a tangent or cotangent function, it would be pi over b. So that's already tells us there's something to worry about here. Let's go ahead and find the inverse sine of both sides. So we have 3 theta equals inverse sine of a half. And again, we know this is what? What's the inverse sine of a half? Thinking out loud that at this point, when we get to the exam, when I ask a question like that, you either has to just pop up in your head, or you have to like draw a little circle, say, all right, the sine, that's the opposite over the adjacent, that's a half. That triangle looks like a 30, 60, 90 triangle, that's 30 degrees, or pi over 6. You have to be able to do that right away. You don't have to answer in class, but you need to be able to do that. I mean, there are other ways, there are other tricks you could use. You could plug it in your calculator and in degree mode recognize, aha, 30 degrees. But you need to be able to figure this out pretty quickly. All right, so it's tempting at this point, pi over 6, to just say, okay, well, wait a minute, there's another solution, right, for sine. The other solution would be 5 pi over 6. It'd be tempting to say, okay, 3 theta is one of those, so theta equals pi over 18 or 5 pi over 18. And then you might be tempted to say, yeah, so it's pi over 18 plus 2 pi n, or 5 pi over 18 plus 2 pi n. But then you would miss out on something. You either have to realize right away that sine of 3 theta is not period 2 pi, it's period 2 pi over 3. That would be one way to look at it. Right? Another way that avoids that step is you just say from the start, wait a minute, 3 theta is pi over 6 plus 2 pi n. That's a correct statement because sine of 3 theta, the sine of something has period 2 pi, and likewise it can be 5 pi over 6 plus 2 pi n. And now divide, right? Now we divide this out and we see theta is pi over 6 plus 2/3 pi n, or 5 of 18, excuse me, or 5 pi over 18 plus 2 pi over 3n. So this problem has a lot more solutions within just the unit circle 2 pi. Seems to have 6. All right, any questions about any of this? I guess the thing to see is we're taking two skills here. One skill occurs when we have a very simple equation to solve with an inverse trig function. But the other skill is all those techniques we have for solving an equation with an x in them, right? So, for example, if I wrote something fairly complicated, like we say, sine to the 4th theta plus 2 cosine cube theta plus cosine squared theta plus 2 cosine theta equals 0. Well, that looks pretty ugly, but if I think of it this way, x to the 4th plus 2x cubed plus x squared plus 2x. Well, what can I do with that? I could take out an x cubed plus 2x squared plus x plus 2. This makes me think maybe I should try grouping. So this is x squared plus 2 plus x plus 2. Did I do that wrong? X squared times x plus 2. So this becomes x squared plus 1, x plus 2 equals 0. Now I look, I see this is, x was just my cosine, so I have cosine of theta equals 0, cosine squared theta plus 1 equals 0, and cosine of theta plus 2 equals 0. And then I just look at these and see what solutions I have here. So again, all this kind of stuff isn't what we've learned now, but you still know this. You could still use this in these types of problems. All right, that's all I have for today. Thank you.